Hello and welcome, SFU Math 232, it's Brenda. Then we're doing section 4.1, Determinants and Cofactor Expansion. So let's get a handle on what these things are. We have seen this a little bit when we tried to calculate an inverse of a 2 by 2 matrix. When we not just tried, we actually did calculate an inverse of a 2 by 2 matrix, and we did use a determinant then. So a determinant can be used, maybe you can think of it as determining several things. The solutions to AX equals B, to figure out whether a matrix is invertible or not, and computing the inverse. So let's just recall that we have a 2 by 2. If we have a 2 by 2 matrix like this, this guy here, we have a 2 by 2 matrix, then we're going to define the determinant to be this number right here. A1 times A11, excuse me, times A22 minus A12 times A21. So what we want to just note here is, I'm going to just draw a couple of lines here. It is this product with a positive sign, and then the next set of numbers is these two numbers here with a negative sign. Okay, so we saw this in the calculation of the inverse. Okay, let's just do an example with a matrix with a 2 by 2 matrix with some numbers in it. This is an important concept. You'll definitely want to know how to calculate determinants. Okay, so there's my favorite matrix, and we will calculate the determinant of this matrix, which we will denote in this manner. You notice that the bars are just straight bars looking like the absolute value signs. So we want to, we will be using that. That means the same as this, determinant of A. Okay, and then we're going to calculate this. It'll be 1 times 4 minus 2 times 3, and that is minus 2. So the determinant of A is minus 2. Now what we want to do is to be able to do this for more than 2 by 2 matrices. In fact, we want to be able to do it for any size matrix that we see. So we're going to come at this in one way to sort of get a proper definition of what's going on using permutations, and then we're going to see how we're going to effectively compute it using cofactor expansion. Okay, so let's just take a look at what the determinant of a 3 by 3 matrix looks like, and it's a little bit tedious to write out, but I will do that, and then we'll see how you can come up with this in the 3 by 3 case, and that is the determinant of this matrix here. This 3 by 3 matrix A here is this A11, A22, A23. Sorry, let's. I hope I don't make any indexing errors. A33 plus A12, A23, A31 plus A13, A21, A32, and then minus A13, A22, A31 minus A12, A21, A33 minus A11, A23, A32. Okay, so that is, you could use this formula to calculate the determinant of this 3 by 3 matrix. You should memorize this. No, I'm just kidding. Actually, I'm totally kidding. We're going to see a way that we can regenerate this quickly and easily. So no, you do not need to memorize this. These things that are listed here, we're going to see some vocabulary. There is a lot of vocabulary in this course. These things here, and I have the plus sign in there purposely. So any of these things here are called assigned elementary products. So these are the signed elementary products of a 3 by 3 matrix. Okay, so one way of doing this, and this only works for the 3 by 3 matrix, so don't generalize this, but I'll show you something we can do here to get these, to regenerate this formula. I will write, I'm attempting to compute the determinant of this 3 by 3 matrix, so here it is. Okay, that's what I want to calculate determinant and do. What I can do is copy the first two columns afterwards here. So I'm just copying here, making a copy of column 1, and I'm making a copy of column 2 beside. Okay, so then I am going to be able to generate the positive terms in this manner. This one here, okay, that guy there, that product. So I'm thinking of going this way. So that's A11, A22, A33. That's that guy right there. And then I can draw the line, a positive one in this direction. That is A12, A23, and A31. That is this guy here. And then I can draw the final one. I can draw on a diagonal through 3. I get A13, A21, A32. I get this guy. Okay, then I can do the diagonals in the opposite direction, and then I consider these ones the negative. Just it's exactly sort of analogous to that 2 by 2 case we did above. So I come through here, and I get A13 times A22 times A31, this guy. Then I come through here, A11, A23, and A32. So that was this one. I just momentary pause there. They're not in exactly the same order. And then minus this one here, A21, A12, A21, A33, this guy. So that's there. I can get all 6 of them simply by taking the first 2 columns and repeating them over and then drawing these appropriate diagonals. So that is a potential memory aid. So you don't have to memorize the formula, and we might not be doing it this way anyhow, but you should see this. Okay, so let's just do an example with some numbers. So I decide I want to calculate the determinant of this matrix here. -1, 0, 1, 2, 1, 4. I duplicate the columns just on the outside here. 2, 0, 1. The first 2 columns, and then I am going to come through here taking the positive products. So that gets me 1 times 0 times 4, that is 0, plus 2 times 1 times 2, that is 4, plus 3 times -1 times -1, that is -3. I see, I'm just circling. I see an arithmetic mistake in my notes. Okay, then I'm going to go on the minus ones, and I am going to get 0 right there. 3 times 0 times 2, I get a 0. So that these ones are all going to be negative, and I get a 0. And then I get 1 times 1 times 1. That's that guy right there. And so that's the 1. And then I get -2 times, -1 times 2 times 4, I get -8. Okay, and then I hope that I don't make arithmetic mistake, so I get 1 minus, and then what do I have in here? 0 plus 1, that's -7. And so I get 1 plus 7, and I get 1 plus 7, I get 8. Okay, so the answer is 8. Now I want you to just notice something. Each product, so by that I mean each one of these products, like there's 6 products. Each product has one number from each row and one number from each column. And multiplying by 0 is easy. So seeing lots of zeros can give you a sense of relief when you're trying to calculate a determinant. Okay, now I'm going to introduce an idea, and this idea is important from the sense that this is the definition. We're going to use this idea of permutations as the definition of the determinant. Okay, so we have a permutation, and a permutation is simply a rearrangement of the numbers that we have, and we have permutations divided into even or odd permutations in accordance with whether the minimum number of interchanges required to get it back to the original order is even or odd. Okay, so let's just see what's happening here by example. So we're going to look at all of the permutations of 1, 2, 3. So this should be all the different ways we can order 1, 2, and 3. So I mean, we could just we can just leave it alone. That's one. That is an even permutation because I have precisely 0 operations to do to get it back to 1, 2, 3. Okay, so let's look at the next another permutation, 1, 3, 2. Okay, that is a permutation of 1, 2, 3, and I did this by swap 2 and 3. So I did one operation, so it would take me one operation to get back to the original. So this one was an even permutation because it's 0 operations to get back, and this one is an odd permutation. And we're going to do them all. So let me get another permutation here, 2, 1, 3. In that permutation, I swapped 1 and 2. Okay, so it's going to take me one permutation to get back to the original ordering. So that one's odd. Let's do another one, 3, 2, 1. And that is a swap 1 and 3. Okay, and so that is an odd permutation as well. Okay, let's take a look at another permutation. That would be 2, 3, 1. Okay, so what do I have to do? Swap 1 and 2, and then I have to, after that, I have to swap 3 and 1. Okay, so this one, it takes me 2 operations to get back to the original ordering. This is an even permutation because 2 is even. Okay, then the final one is 3, 1, 2. And that is also going to be an even permutation. I have to swap 1 and 3. I'll put that for swap 1 and 3, and swap 1 and 2. That's an even permutation. So a few things to notice right off the top from this example, which is true in general. That is the number of permutations. I've got them all here. There's 6 of them. The number of permutations is 6, which is 3 factorial. If I was to have n numbers, it would be n factorial. Okay, there's that. And then you'll notice that half of the permutations are even and half are odd. Half are even and half are odd. Okay, so I'm asking you to as an exercise, do the same thing for 1, 2, 3, and 4. Okay, there'll be 12 of them. 4 factorial is equal to 12, so you'll find 4 of them. This takes a little bit of time. It's a good exercise to do this once in your life. Make sure you can do it. And also now, at this point, little alarm bells should be going off that the computation is going to get extremely laborious as we go because the factorial grows very, very fast. Okay, so that is a permutation. Now we're going to use that to get at all of the elementary products. So we have some product here, some a multiplication of some of the entries of our matrix, and what you'll notice here is that the row index here is 1, 2, etc. to n. So the row index looks like this. I don't know if I really want it in the set notation, but the row index is like this: 1, 2, 3, ... It is the numbers from 1 to n in the natural order. And then the column index on this product here, the column index, is a permutation of the row index. And whenever we have a product like that of the elements in your matrix where the row index is the natural ordering of the numbers from 1 to n and the column index is a permutation of the numbers from 1 to n, then we call that an elementary product of the matrix. Again, let's take an example at what this what this looks like. So we've got, we know from what we've done before on a 3 by 3 matrix, we have 6 elementary products. Well, we know we have 6 permutations, and this means we're going to have 6 elementary products. So we're going to write the row index, so I'm going to fill in the column index, but right now I'm just indicating the row index. It's always going to be like that. The row index is 1, 2, 3. The row index on all 6 of them is going to be 1, 2, 3. So I'm simply going to write this out 6 times. This is the row index in each case. 4, 5, 6 times. Okay, and then now I'm going to just look at my permutations, and I will put one of my permutations onto as the column index in each one of these. And I already know what the permutations are. I've already put them above. So now I'm filling in the second index here with each one of my permutations. So one of my permutations was 1, 2, 3. One of my permutation was 1, 3, 2. Another permutation was 2, 1, 3. Another one was 3, 2, 1. And 2, 3, 1. And 3, 1, 2. Okay, this one was even. These 3 were odd, and then these 2 were even. Okay. And then I'm going to point out here, -1 to an odd number is negative, and -1 to an even number is positive. And so we will see that I've now written out all of the elementary products, and some of them are even and some of them are odd. And I'm going to identify the ones that are odd. I'm going to put that minus sign in front of those ones. And the ones that are even, I'm going to be putting the positive sign in front. So now those are the signed elementary products. Okay. So here we have that written out here. What is a signed elementary product? That is the any one of these products where the where the row index is from 1 to n and the column index is a permutation. And with that plus or minus 1 in the front there, it's called the signed elementary product. Okay, so we've in fact already done this. Let us just write it out. Find all the signed elementary products for the 3 by 3 matrix. So we want to ensure that we understand we have got this one, okay, so those are the ones associated with the even permutations, and then we had these ones. Those ones associated with the odd permutations. So those are all of the signed elementary products of our matrix. And then now that we've got that in place, that is simply the sum of all our signed elementary products is what we define to be the determinant. So in the general case, if we've got an n by n matrix, so we've got here an n by n matrix, then the determinant of A, which we can denote this way or this way, and it's the sum of all the elementary products. So that is what this thing right here is telling us. The determinant of A is the sum over all the permutations of the signed elementary products of the elements in the matrix. Okay, in general, we will not be computing the determinant this way. It is the definition. So normally what you do is, you have a definition of something, and then any other way that we have of calculating this, we need to prove that it is equivalent to computing it from the definition. We may not actually do that always in this lecture, but at some point that needs to be done for proper rigorous treatment of the thing. You define something which we have now defined called the determinant. We have defined it in this way as the sum of all the assigned elementary products. And then if we're going to calculate it in a different way, like we're going to calculate it, for example, by cofactor expansion, we have to be sure that that calculation, of course, yields the same number every time. Okay, let us now proceed to calculate the determinant of a 3 by 3 matrix using the definition of the determinant. That is by evaluating the signed elementary products. Okay, so this is a time-consuming procedure. So maybe stop the video, actually, do it yourself, and then fast forward through me doing it, and then see if you got the same number. Possibly catch an arithmetic mistake by me, or figure out how to make sure you know how to do this yourself. Okay, so that is 0. So that's my first signed elementary product. So I'm going to be going through them all like this. These ones are this. I'm just going to emphasize that these are the positive ones. So I have the even permutations that I got to be 3 times 4 times 4, which is 16 times 3, I got 48. And then I have A13, A21, A32. And when I plugged in the numbers for that, I got 1, 5, minus 8, that's minus 40. Okay, and then the negative signed product, so that's going to be minus A11, A23, A32, and that's minus, and then I multiply the numbers together, minus 2, 4, minus 8, that is minus 64, and minus A12, A21, A33, minus 3, 5, 0, 0, and then minus A13, A22, A31, and that's minus 1, 1, 4. Minus 4. Then I add all of those numbers together. So I'm adding them all together. This is that summation. And I get minus 60. Okay, so the determinant of this matrix right here is minus 60. Okay, a couple of notes before we move to how to do the cofactor expansion. What is the determinant of a matrix with a 0 row? It is 0. It is 0. Okay, think about this. Each product has one number from each row. Right? So, I mean, since each product has a 0 in it, the whole thing is 0. All the products are 0, and the sum of a bunch of zeros is 0. Thing is 0. So, if you see a 0 row, you are, for that matter, a 0 column, you can just immediately write down the result. You don't have to do anything. Okay, so now what we're going to do is take a look at what the determinant is of a triangular matrix. Actually, what we're going to do first is just take a quick look at the diagonal matrix, and then we'll take a look at the less restrictive case of the triangular matrix. So let's just take a look at a diagonal matrix first. That looks like this. Okay, it's I think pretty clear to see that there's only one elementary product that has all entries that are non-zero. So in this case, the determinant of A is 1 times 2 times 3, the product of those elements on the diagonal, which is 6. Okay, so all the other products will contain at least 1 0, so we're done. So that is actually true also of the upper and lower triangular case. Let's just take a look at the upper triangular case so we can see how that looks, but this is true of the lower triangular case too. There's the upper triangular case. Now I imagine myself maybe doing it in the method of what we saw on the first slide here. That would be duplicating this column and then duplicating the second column. And then I'm going to look at what those diagonals are giving me. So these are the positive diagonals here along here. Then I see there's a 0 in that product, and there's a 0 in that product. Okay, so the only non-zero product right now is 1 times 4 times 6. Now I'm going to go the other way. different color, and I've got a 0 in that product, I've got a 0 in that product, and that's with the 1 there. And then I've got a 0 in that product. Okay, that will always happen. It doesn't matter which numbers there are. Because of where the zeros are, this always happens. So the determinant of a triangular matrix, upper or lower, is the product. So the answer here is product of the diagonal entries. So upper and lower triangular matrices are very nice. Okay, now we're going to come to a computational method of finding the determinant of an n by n matrix. And in order to talk about that, we have to introduce some more words. And those two words here are the minor and the cofactor. And so what are these things? So if we have a square matrix, then the minor of entry aij, which we're going to denote by minor a sub ij of A, is defined to be the determinant of the submatrix. So this is a smaller matrix obtained by removing the ith row and the jth column. You can tell which row and column to remove because it's indexed right there. And then the cofactor is very similar to the minor, but we are going to multiply by -1 times the sum of the row and column index so that we have the right sign. Okay, so let's just take an example. Okay, here's a matrix A, my favorite matrix. Okay, there's a matrix. And let us attempt to calculate the 2, minor. Okay, so in this case I have I is equal to 2 and j is equal to 2. So what I'm going to do is take a pencil and I'm going to cross out the second row and the second column, and then I'm going to have that the minor, the 2, minor of A is the determinant of what's remaining, the submatrix. Those are these numbers here that didn't get crossed out, which I can compute because it's a 2 by 2 matrix. So I say 1 times 9, 1 times, so this is equal to 1 times 9 minus 3 times 7. That is 9 minus 21. Yeah, what is 9 minus 21? Let's see, that is minus 12. Okay, so that is the, sorry, I'm thinking here. So that is the 2, minor, and then what I do is I add up I and j, and I get 4. So I plus j in this case is 2 plus 2, and that is 4. So then the C22 is -1 to the 4 times -12, and that is going to be -12. Okay, so I mean C22 and M22 like that will be the same number, but possibly a different sign, possibly not. Okay. That is an example of computing a minor and a cofactor. So it is the case that we can compute the matrix, the determinant of a matrix, by multiplying the entries in any row by their cofactors and adding the resulting products. So we're saying here that the determinant of A is equal to cofactor expansion along the jth column. That's one option. Or it can be equal to cofactor expansion along the ith row. We formed this formula. I think this is much easier seen with a couple of examples, which we will get to shortly. But let us just take a look at one thing first, and that is Cij of A is equal to -1 to the I plus j of Mij of A. And -1 to the odd is equal to -1, and -1 to the even is equal to 1. Okay, so I'm going to draw a matrix of no particular size, and I'm going to notice, for example, the this factor here, whether I multiply by -1 or not, is going to that answer is going to come to a no right here. This one is always going to be positive. Why? Because right there, for this entry right here, I equals 1 and j equals 1. 1 plus 1 is 2, and -1 to the 2 is 1. And so that similarly, this will be minus, plus, minus, and it will continue across like that. So let's take a look at, for example, this one right here. I is equal to 1 and j is equal to 2. 1 plus 2 is 3. -1 to the 3 is -1, so that one there is negative. Similarly, it looks like this. So you can do a few of these and just assure yourself that what I'm giving you here is this factor based upon that position where I'm putting the plus and minus in this matrix. It just keeps going. Okay, so it's that continues. Those are the signs of the cofactor. Okay, let us do this now. This is likely how you will compute these guys by hand. There are other ways of doing it, but this is a good sort of first way of going about this. So we're going to find the determinant of A using cofactor expansion along the first row. Okay, so what we do is we go along the first row. So I'm thinking of doing this cofactor expansion along this first row. So the first thing I'm going to have is the positive sign. That is the -1 to the 2. And then I'm going to have the -2. That's that element. And then I'm going to be thinking like this, removing the first row in the first column, because I am right now calculating M11. And so what is left? The determinant of 1, 4, -8, and 0. Okay, then I move along to the next. So I just did that one. Now I move to this one here. Change the color. I move to this guy here, 3. And it's minus 3 times the determinant of, and I cross out the first row and the second column because 3 is in the 1, 2 position. Okay, and what is left? 5, 4, 4, 0. Then I move to the next number, the 1, and that is plus. So it's plus, minus, plus. There's a 1, and then I cross out these two rows and I use the other ones. 5, 1, that row in that column. 5, 1, 4, -8. These are 2 by 2 determinants. I can compute those. -2 times 32. That is 1 times 0 minus 4 times -8. So these are the 2 by 2 determinants I'm computing here. Okay. Then I add all those numbers together and I get -60. So check back. This is the same answer as using the signed elementary products. So check back. Same answer from earlier using the signed elementary products. Okay, so I would sort of set myself up to do this way. I did it along the first row. Okay, we don't have to do it along the first row. We can do it along any row or any column. So now I'm going to just do it again. Normally you wouldn't do this, of course, you've already got the answer, but I want to show you that it does not matter. So for example here, and you are going to want to be intelligent about which choice you make. So let's just put the matrix here again. There it is. Okay, now I'm going to do cofactor expansion along the third column. Okay, so I am going to do the cofactor expansion here along the third column. So I do exactly the same procedure. This is plus, minus, plus, and then this is this third column here. That's the first row, and then that's plus, minus, plus coming down here. So I am 1 times the, and then I imagine crossing out the row in the column that contains that 1, and I get 5, 1, 4, minus 8. And then I come down the column and I get the 4 there, and it's minus. That's the minus, and I get the 4, and then I imagine crossing out the row and the column containing the 4. That leaves me with the 2, 3, 4, minus 8. And then I get plus 0, and doesn't matter what this is, because it's multiplied by 0. This is the huge upside of choosing the row or the column that has the most number of zeros in it. Okay, so that is a strong suggestion to always do that. Choose the row or column that has the most zeros. So now I make this calculation. I get minus 44 minus 4 times 4, and that is equal to minus 60 as before. But that was easier to calculate. I had one less addition and a couple of less multiplications. Okay, so there it is. You can see it's quite interesting. So I mean, when you look at this here versus this here, it's not the same numbers in these matrices, and yet, right? It always comes out to be the same number. Okay, so there's a message here. Zeros are your friend. Make use of them. Okay, let us do then the final example, which will be to do a determinant of a 4x4 matrix using cofactor expansion. So what are we going to do? We're going to take a look. We're going to pause before like jumping into the calculation. Pause and think and to say to yourself, which row or column should I expand on? Which basically is the question of which row or column has the most number of zeros. And so I see that column 2 is the way to go, because column 2 has 3 zeros in it. And so that will reduce the calculations immensely. So so I'm going to now write this out. It's going to be minus 0 times the determinant of something. I don't care because it's multiplied by 0. Plus 1 times the determinant of, well, I cross out the row and the column with that 1 in it, and I get 1, 0, 3, 4, 0, 1, minus 2, 7, 1. And then I would be plus 0 times something. I'm not even bothering to fill this in, right? And then minus 0 times something else. All these guys are 0, so I don't have to worry about them. Now I have boiled down the calculation to finding the determinant of a 3x3 matrix. So I mean, if there's all numbers in here, I'm going to have to make four. Now I'm going to have to, going from a 4x4 matrix, I am going to have to make up to 4 calculations of determinant of 3x3 matrix, and then for each one of those I'm going to have to make 3 calculations of the determinant of a 2x2 matrix. It's a recursive procedure. You keep going until you get down to the 2x2 case. So now I'm here. Luckily this number is a 1, so I don't have to worry about carrying that anywhere. And I look now and I'm like, which row or column has the most number of zeros? Because I'm going to have to do the cofactor expansion again on this 3x3 one. And I see that I should be here, right? And so then I'm like, okay, I'm going to do the cofactor expansion there on that second column again. And what's that going to look like? It's going to be minus, because we're in this position right here, minus 0 times something. I'm not going to worry about it. Plus 0 times something else. Okay, that counts for that number and that number. And then it's going to be minus 7 times the 2x2 determinant formed by crossing out the row and the column with that 7 in it. That is going to be 1, 3, 4, and sorry, hang on. Yep, 1, 3, 4, and 1. I think I see an error here in my notes. So I'm just going to now verify because 7 is in that 007, 311. Just checking my numbers a bit here. Yep, so I'm crossing that out. I've got 1, 3, 4, 1. And so that is going to be minus 7. Now what is that determinant? 1 times 1 minus 3 times 4. Okay, so that is minus 7, 1 minus 12. And that is going to be minus 7 times minus 11, and that is 77. That is my final answer. Okay, so if you wanted, hammer home the idea that choosing the row or column with the most zeros is a good idea, you could try the whole problem again, right? You could try this problem again by expanding, for example, along the second row. Like you do it like that, expand along this row. Go ahead and do that, and then you'll see how many more calculations you need. And if everybody's done the arithmetic correctly, of course you'll get the same answer. Okay, that is the conclusion here of section 4.1. So the important messages here are that there is this thing called the determinant that is defined using signed elementary products, which in turn rely on understanding what is a permutation. And then we have alternate methods of doing the computation, and this cofactor expansion method is quite a good one. That's all for now. I'll be back with section 4.2 shortly. Bye.